Hi, all you sake lovers out there. It's time once again for another episode of Sake Science. And if you've drunk a lot of sake, I'm sure you've noticed how acidity can really influence the overall presence of a sake. And in recent years, many brewers have been looking to adjust the level and relative proportions of the different acids in sake to give it some special character. But like many things in sake, this is an issue that is filled with some misinformation and maybe some misconceptions. What acids are important in sake? Where do they come from? How does their perception change when paired with different foods, at different temperatures, or with aging? Find out the answers to these questions and more as we take a closer look at organic acids. So first of all, what organic acids are really important for the flavor of sake? Here's a chart that shows the average values for 30 different types of sake of the 6 most common organic acids. These are pyruvic, acetic, citric, malic, succinic, and lactic. And you can see that malic, succinic, and lactic compose the majority of organic acids present. So those are the 3 that I'm going to be talking about most today. Now what's interesting is how the amounts of these organic acids compare with those in wine. On this chart we can see in the light blue are the levels of the average values of organic acids in sake, and these are in the ballpark of what we can expect from wine with the dark blue bars. And as you can see, the levels are of all of these organic acids are much higher in wine. And wine also has one organic acid that is not present in sake, which is tartaric acid. And this is a little bit important, and we'll be talking about it a little bit more later. Now, I have a question for you. Just off the top of your head, where do you think the majority of organic acids present in sake actually come from? Well, here's a breakdown of the general source of the majority of the organic acids present. And we can see that 4% of the acids come from koji, about 6% come from the kakemai or steamed rice, an additional 17% comes from the shubo, and that doesn't change depending on whether that's sokujo or kimoto or yamahai. That's basically about the same level for any kind of moto that's used. And then the vast majority of organic acids that are produced in sake come from the yeast in the main fermentation mash. And this is a really important point to understand. The proportion of the 3 main organic acids that are present in sake are overwhelmingly produced by the yeast. Over 50% of the lactic acid and over 90% of the succinic and malic acid are produced by yeast metabolism. Now, yeast metabolism is really complicated, but the really important thing to understand is the vast majority of organic acids produced in sake ultimately come from glucose. And one of the main pathways for that goes through the intermediate known as pyruvate or pyruvic acid. And then there are 3 pathways that branch off from pyruvate. One goes through acetaldehyde, and that also goes on to alcohol fermentation, but if it doesn't go on to alcohol fermentation, the acetaldehyde can be turned into acetate or acetic acid. Another pathway is anaerobic fermentation that produces lactate or lactic acid. And then a third pathway goes through the tricarboxylic acid cycle, Krebs cycle, or citric acid cycle. The cycle that's so important they named it 3 times. And this cycle is the source of most of the malate and succinate, or malic acid and succinic acid in sake. Now the amounts and proportions of these different organic acids are affected by lots of different factors. For example, I had to write it down so that I remembered. For example, not only the yeast genetics, but the temperature, the proportion of koji versus kakemai, the proportion of water used in brewing, the timing of alcohol addition in the case of aruten sake, the total fermentation time, and even whether the sake is pasteurized or not. So now I want to take a little bit more time to talk a little bit more in depth about malate and succinate in particular, because these are the two acids that brewers are really looking to in recent years to kind of give some special character to their sake. And here's a really simplified version of that citric acid cycle. One way that this cycle can go is clockwise on this diagram. And that happens under mostly aerobic conditions at the beginning of the main fermentation. And in this pathway, pyruvate is changed into acetyl-CoA and then enters the citric acid cycle by reacting with oxaloacetate to form citrate. And then the cycle goes around in a clockwise direction, forming succinate, malate, and then back to oxaloacetate, and then around again. And this oxidative direction of the cycle is responsible for producing over 50% of the succinate or succinic acid present. But in the mid and late fermentation, the cycle can actually go in the other direction, the counterclockwise direction. And this is the reduction direction. In this case, pyruvate is directly turned into oxaloacetate, and then that oxaloacetate is reduced to malate and then on to succinate. Now, the formation of oxaloacetate from pyruvate takes place through an enzyme called pyruvate carboxylase. And then malate is formed from oxaloacetate by an enzyme called malate dehydrogenase. And then there's another entryway into this cycle through another cycle called the purine nucleotide cycle, which produces fumarate as one of its products. And that fumarate can then be transformed into malate or into succinate. So the reason why I've gone into a little bit of explanation about this cycle is that it offers a lot of entryways for researchers to create new types of yeast with special metabolic properties to produce more or less of malate and succinate in sake. And so I want to talk a little bit about how the taste of these organic acids is actually quite different. So for example, with lactic acid, it has a kind of tangy and rounded flavor, which is characteristic of yogurt. For succinic acid, it has a rich and somewhat bitter flavor, and it's present in large quantities in shellfish. Malic acid has a distinctive tart and sharp profile and is present in sour apples and grapes. And citric acid is probably most common to many people for its kind of burst of sour freshness and is present in many citrus fruits, including lemons. So let's take a look at a couple of yeasts that have been developed to have some special properties with regards to the amounts of organic acids they produce. The first is a high malic acid producing yeast that's a chemically induced low maltose utilizing mutant of Kyokai 701. And this has a higher expression of that malate dehydrogenase enzyme that forms malate from oxaloacetate. As we can see, it is capable of producing almost 5 times more the amount of malic acid and a comparatively lower amount of succinic acid. This means that it's fresh and sharper and less bitter than the regular sake made with K701 yeast. The next is a natural mutant of Kyokai 901 that has been isolated with the antibiotic cyclohexamide. And you can see this mutant yeast produces relatively more amounts of both malic and succinic acid, giving it an overall more acidic profile. Now there are actually a lot of different high malic acid producing yeasts available these days, and they're increasingly popular. And so we can find high malic acid producing varieties of a lot of very common yeasts and even yeasts that have been developed by breweries themselves. And here's an example of one of those. This is a sake called Fuwaru Shiro, and this is from Ishikawa Brewery in Tokyo. And the name of the brand is Tamajiman. And this is interesting because there are three versions that are released. One in spring is the Nama Nigori, and the second one is released in summer, and then the third one is the Aki Agari, which is released in fall. Anyway, let's take a look at it. So you can see it's lightly cloudy, Nigori, and so it's not excessively fruity in the nose. There's some light fruit, and to be honest, there's a little bit of yogurty diacetyl, but it's not at a level that it really bothers me in this. Sometimes it does, but I think this is actually kind of contributing to the nose because it doesn't have a strong fruity odor of its own. Mmm, delicious. Wow. I mean, it's sweet. Um, there's just a little bit of fizziness to it. And the acidity is quite forward, really fresh, really crisp. And even though it's sweet, it doesn't, linger on the tongue. It's very clean, clean finish. Now, when it comes to pairing something like this, I like to think not only about the overall level of the acidity, but when there's one specific organic acid that stands out, I like to think about how to pair it given the fact that these organic acids also resemble certain foods or seasonings. So for example, with sake that has a lot of citric acid, and if you noticed, I haven't talked about that a lot today because uh, sake with a lot of citric acid, in that case, it usually comes from the koji, and so I'm going to be talking about that in a video on koji. But anyway, I find that pairing sake with a lot of citric acid works well with things that can use a little splash of citrus or lemon. And then in the case of a lot of lactic acid, I like to pair that with things that can go well with other fermented seasonings that have a lot of lactic acid. So with something like this that has a lot of malic acid and is on the sweet side, it reminds me a lot of apples and also of kind of like a sweet cider or a very sweet Riesling maybe. And so I might pair it with things that go well with things like that. So for example, maybe chilled pork roast or goat cheese or galette bretonne or maybe even a dessert with cream and fruits.